Okay, I trust everyone can hear me. Or somebody can hear me? Good. Alrighty. Yeah, so this is going to be the final lecture of the course. The final lecture of content. We're going to have a review lecture. And then also just a reminder, this Thursday is going to be the makeup recitation. So you can make up one recitation. But when you make up a recitation, you have to be able to do every problem on the recitation. So the claim that you'll make on Thursday will just basically just be a number between 1 and 4, 1, 2, 3, or 4. And then that will basically mean that we're free to call upon you to do any problem in the corresponding recitation. You'll get full points for the recitation by doing that claim. And I hope that's clear. Is that clear to people? Or if there are any questions, just fire away. Okay, so now, yeah, just any questions, put them in the chat or send them to me in a private chat. So now today what we're going to cover is the first part we're going to cover are views and indexes. And then the second part we're going to cover is transactions. So these are, so we're back to relational databases now. So we're kind of away from semi-structured. So this is back to SQL. So the views and indexes. So we might as well just kind of go and these are very useful, very, very useful. So let's start out with views. What is a view? Okay, so a view is basically, it's a way that you can define a virtual relation, basically. So what a view is, we have a good example here of a view. It's this, when we consider this, this drinking example that has been developed throughout the course, we could maybe have a view called can drink, which would mean that the drinker frequents a bar that sells a beer. So that means that you can't drink a beer that if you're only if in this modeled reality here, if a drinker is going to visit a bar, they can order a beer at that bar. So the only beers they can drink that they can reach basically are beers that are being sold by the bars that they frequent. Okay, so that you could have a table maybe where you would actually just kind of put that into the table, but that would maybe lead to redundancies and weirdness. You have to do a lot of management to make sure that table was being kind of kept up to date. So for instance, we have all the people, if we were going to maintain a table called can drink, the drinker and the beer, then anytime the drinker says they're going to frequent a new bar, then we have to add a whole bunch of beers to what they can drink. And likewise, when a bar adds a new beer they're selling, then all the people who frequent that bar have to have that beer added to can drink as well. So that's really not very workable. So the way this works in SQL is you do something like the following. You basically say create view, and then you give it a name. So let's create the view can drink. And then what's elegant here is that you just then you just give an SQL statement. All right, so this right here. So just forget the create view can drink as here, and just look at this right here. You guys know what this thing does, right? Select drinker and beer from the tables frequents and sells, where we're just simply doing a join. All right, so we're just doing a join over frequents and sells, and we're projecting out the drinker and the beer. All right. So that right there is just, that could be a fairly large table or a fairly large result. But what we're doing then is we're just basically defining, we're creating this view can drink, which is defined as that. And then what happens is if you actually use the can drink, so here's an SQL statement here. So I say select beer from can drink where the drinker is Sally. So now what SQL does under the hood as an operation in solving this SQL statement here, what it's going to wind up doing is it's going to go to this can drink here, and it's going to unfold it and substitute in an intelligent way. It's going to substitute in this actual SQL statement. All right. So what that means then is that frequents and sells, these are what are called base tables. So these are tables that actually hold data, right? And this canned drink is a view. But what happens when the SQL engine tries to solve this query or solves this query here is what it does is it takes the canned drink and it just expands it into this thing right here, the select drink from, it basically does a subquery doing this. So what that means is it means that views are basically reconciled, or they're basically expanded out to base tables. So I hope that's clear. So that's what a view is. It's all it is. Actually, views are really easy to implement. All right. It's very easy to implement a view mechanism in a database because all you do is anywhere you see the view in any query the user puts together, you just expand it. You just kind of just do a syntactic expansion at that point, and you just expand it with the view definition. Okay, so it's a very elegant and quick way of kind of enhancing, the set of predicates or the set of the vocabulary of what you can ask over the database with these kind of virtual tables. All right, so that's what a view is. So these come in. These come in handy quite a bit. All right, so you'll see people use views quite a bit. Again, it's mostly just to kind of give it so that that there's a little bit more. It makes writing the queries easier because you can kind of lift things up to a more kind of abstract conceptual level. And then you can ask the questions over those more abstract tables, which are actually just views, and they get expanded out to the actual base tables. Right. So views are very good in that. It's definitely something that's highly used in databases. All right, but we have a different kind of view. So we have the idea of what's called a materialized view. All right, so materialized views are, it's a little bit of extra syntax. Now let me just say what a materialized view is. A materialized view actually goes and actually computes the tables, all right, beforehand. Before any query, it'll actually kind of grind out the tables, right? So in this case of canned drink, if canned drink here had been defined as create materialized view, if there was materialized right here, view canned drink, then what that would do then is that the engine would say, okay, fine, it would create a temporary table basically that would be canned drink, and it would populate that table with it would actually just kind of grind out the result. All right, and then and that would just kind of be held kind of it would be held in the database as kind of, it could actually be saved on disk. It could be basically, it's being held kind of as a full-fledged table, basically. And then what would happen then is when this query was issued here, it would go directly to that table. So the idea here then is that materialized views are just like views, but they're pre-calculated, and thus materialized views are a lot quicker. They're a lot faster to access. Okay, so you get a big speed up. So sometimes you actually do need to build materialized views, and then you have some other additional statements you can make that basically say refresh or rebuild the materialized view. So if I had built this as a materialized view and then I start adding a bunch of other bars that Sally can frequent, then that's going to require that the materialized view gets rebuilt. All right, so you have to do that explicitly. You have to explicitly call for that, or a lot of times you do it as a trigger. Okay, but it has to be maintained. Now, you might think, well, why don't I just create a table called canned drink and then just do a insert select into, right, or insert into, and then the definition of the view. You could do it that way, and in some sense that is a materialized view, but it's just that when you do it as a materialized view, PostgreSQL or the other system will do a little more bookkeeping for you. So it's kind of, it's advised to kind of use the materialized view if you have that in the database, if that's an available option. Okay, so yeah, so these again, the materialized views. Actually, materialized views are very often used as well, especially when you get to larger databases. So you get to a bigger database. Yeah, because you don't want to be recalculating the view every single time. So it cuts down on the computation cost if you're doing materialized views. And then another thing also just to keep in mind here is that you kind of have to think of it this way in the quote real world. There's kind of data that tends to be static. all right, this kind of master data that tends to be static. Okay, it might be added to every couple of days. You might add some more books or something, or some more items in. So it gets refreshed, but it's not happening so often. But then you have like the data where people are actually making orders of stuff, and that stuff is very, very dynamic. So when you look at like the tables that are more static, a lot of times you'll build these kind of materialized views over those to get good speed ups. Okay, because you can, basically, because when they say that the database is down for, or every night at 3 o'clock in the morning when no one's there, or not many people are there, they might take the system offline for a brief moment to kind of rebuild the materialized views. Or they might, well, actually modern systems can allow you to do that concurrently, but it might slow down a little bit because it's grinding away, redoing the materialized views. Okay, so it's kind of like a maintenance step on a daily basis. Okay, I hope that makes things clear, and I hope that it makes sense why the materialized views would be more efficient. All right, so speaking of efficiency, then we've got the whole issue of indexes, or indices, if you want to be correct. I mean, I call them indexes. I call it schemas. I call it indexes. I call it formulas. But I guess what you're supposed to say, if you're being kind of proper, is indices, schemata, and formulae. But I'm kind of a regular kind of guy, and I just do my regular. I mean, I just put regular plurals on stuff. I just put an S on the end. So that's me. But indexes, or indices, if you insist, these are data structures that are built over tables to speed up access. And a lot of these you get for free. So like when you declare something as a primary key, PostgreSQL or MySQL or SQLite or any of the Oracle or whatever, they'll always build an index over the primary key. Okay, that's just going to happen. And the same is going to happen also with the uniques. When you declare uniques, they're going to build an index over that. Now, historically, there's been a lot of different types of indexes, but basically it's come down to it that essentially the winning index strategy is what's called a B+ tree. And what this is, it's just a tree that it has an extremely large fan out. Okay, so it's got maybe a fan out of like 300. Think of it this way: it's got a fan out of 300. So how many levels of the index do you need to do if you want to cover 1 million records, and it's got a fan out of 300, you can basically essentially cover that in something log base 300 of 1 million. And log base 300 of 1 million is not that much. I mean, 2 or 3 or something. I mean, it's so when you're taking something out to a very, very high base log of something, it really, really kind of the access individual records is really, really fast. Okay, so really databases underneath the hood don't use, at least as far as the indexing strategies, they don't tend to use hash tables anymore. They just use these big B+ tree indexes. If you're interested about this kind of stuff and kind of what's really going under the hood and some of the variations and kind of take the advanced database course. So I'll probably kind of put that in as a general advertisement for the advanced course. It's 5D187. The course you guys are taking right now is 5D202. I don't know why the number goes down for the advanced course, but I think it's kind of, in a way, it's kind of funny. But the advanced course will go into great detail over indexes and also how they're used. But we're just going to cover it here and kind of how you can just kind of get at least some use out of them. All right, so when you can declare indexes by, it's not a standard, unfortunately, but you basically can, in PostgreSQL, you say like create index and you give it a name. So that right here, this would be like a beer index on beer in on the beer's manufacturer. All right, the manufacturer, recall, is not the primary key of beers, right? It's an attribute of beers, but what this does right here is it creates a separate or a secondary index on that. So it's not really going to be covered here, but there's 2 different types of indexes essentially. There's a primary index, or what's also called a clustering index, and there's a secondary index or a non-clustering index. And when it says clustering, what it means that actually physically in the database system, when you have the index over an index over like a primary key usually, is a clustering index, because then if you look on the actual system itself, things are being sorted in that order on disk. Okay, so there can only be one clustering index for a table. There can be many secondary indexes, but the clustering one is going to be, there's only going to be one. That's usually going to be on the primary key. There are some different performance capabilities. I mean, if you do things, I mean, on the clustering index, they tend to be faster. But there's nothing that stops you. There's nothing that stops you from not building additional indexes on all on the different attributes. Now, if you look at the second index here, what it has here is it has an index on, and then it has two attributes, the bar and the beer in cells. Okay. So when you build indexes, you can build them on more than one attribute. Okay. So what that builds inside the system is it builds like a tree that the first several layers of the tree will then decide, in this case, bar. And then once you get down to the bar, then before you get to the leaves, then it'll start kind of building on the beers. All right. So when you say create index on a table here, and then you say attribute 1, attribute 2, that is not the same index as attribute 2, attribute 1. Does people understand that? Because if it's bar, if you build an index bar and then beer, then bar is going to be the first thing the index sorts on, all right, sorts on in the sense that the way it provides the navigation inside the index. The first thing it's going to be navigating on is the keys for bar. Once it's done with the bar, then it will navigate on beer. Whereas if you declare this for beer and then bar, it would do the opposite. First, it would be doing the navigation based on beer, and then it would do it on bar. Okay, so it does matter the order in which you do multi-attribute indexes. There's a lot more if you look into like PostgreSQL. There's a lot more fancy stuff you can do on building indexes. You can do stuff like you can have functions inside these indexes. You can have things going to upper, so you're basically doing it on the uppercase version of something. You can have it so the index only looks at maybe the first 4 characters of a string. So inside here, when you can have functions in here that will determine very, very specialized indexes. Okay, so when you get bigger databases, you might actually have to go and kind of fiddle around with these things to kind of get better performance. So better performance is all about like, if it wasn't clear, we'd have this right here. If we build the index on bar and beer here, and then we ask a query here where we want the the manufacturer, we have okay, right here. If we put this query in here, give me the price from beers and cells where the manufacturer is Pete's and the beer, okay, then here's the join condition. And then the bar is Joe's bar. If we have indexes on the manufacturer and also the bar, those can be used to kind of whittle it down. The engine's very smart. It can go and it can whittle it down and just get the bars that are Joe's bars first, and just the beers that are manufactured by Pete's, and then make it so that this join here is a pretty skimpy join because it's really narrowed things down. So it's gone and let's say that there's millions and millions of beers and there's millions and millions of bars. Well, using the index here, we were able to kind of go and isolate the table to a fairly small set and a fairly small, and basically one bar here. And then when we did the join, it was skimpy. All right, and the joins are the big expensive operations. So having an index available is really beneficial. All right. If you want to do this, I think I talked about this a little bit before. Let me put it in the chat here. If you put this in front of all of your queries, okay, I'll just say select and then dot. Basically, explain, analyze. Okay, so this is, if you say explain, analyze, and then you have the SQL after that, you will actually see what the query plan is. So if you've defined indexes over the database, you can see whether or not, or how the PostgreSQL engine is using the indexes by just putting explain, analyze in front of it. And then you'll see what the plan is, and you'll see that what its strategy is to use the indexes to solve the query. So a lot of times you'll do that, and then you'll see that that a lot of times it really gets dramatic speed ups. Because if you don't have indexes here, if you don't have any indexes built, it has to do what's called a table scan. It has to read through the whole table. All right. Now, let's just be honest here. If the number of beers is like 500 and the number of bars is like 300, that is like really, really shrimpy. That's a small little peanut database. And those little peanut databases like that's really a small database. I mean, you can do indexing and you might get some little bit of speed up, but it all depends on kind of what your use case is. So sometimes actually it's just, I mean, the computers are so fast these days. Sometimes you just say, and just be lazy because it works. But if you start then getting to high volume, there's a lot of people question. If the moment you sense any performance problems, you have to address it, because any delay is terrible for people. So yeah, but anyways, indexes is one of the main strategies to do that. And there's a lot of things you can do. So this whole database tuning area is one where you have these experts who can really, I mean, they really do need to speed things up. I mean, it's you get big high volume databases where a lot of things are going on. Then you need to start looking at the kind of what's the mix of queries that are coming in, and you need to kind of determine what indexes to build over, and then you do that, and then you test it, and you see kind of how it works, and then you kind of jiggle it around a little bit and see, if it it's a little bit of like a black art, because you just kind of it's not really so I mean, you can try to model a little bit. But on that note, let me just ask a question to everybody. So let's say we have this database. It doesn't really matter what it is, but let's say it's a big database, big-ish. It's got maybe 10 or 20 million tuples. Okay, so it's not, it's not a peanut database. It's fairly big. And we have a lot of queries that are coming against it. So, and also, we're updating, we're adding a lot of tuples in, we're taking a lot of tuples out. It's a fairly active read and writes and all that other stuff. But we want to have it so it's really fast when people query it, right? And so let's say it has 10 attributes. Okay. So why don't I just build something on the order of 10 factorial different indices? Because then it would really be fast, right? So I'll build all the orderings over the attributes. I'll build indexes over all of those. Do people understand what I'm proposing? I mean, we have a database that has one table, it has 10 attributes, and it's a big table, it's deep, right? Deep meaning that there's a lot of tuples. They're being read and written, etc. And I just say, I want this thing to be fast. So I say, I'm going to build just a ton of indexes, basically something on the order of 10 factorial different indexes. Because then whatever combination of conditions in the query, it's going to snap up really, super speed. It's going to snap up the right tuples. Does anybody have any criticism about that approach? Is that good? I mean, should we do that? It could be a problem. I mean, what's wrong with that? Is there anything wrong with that? I guess I'll go ahead and do it, right? Or do you want me to do it? What should I do it? Okay, so some people think it sounds, yeah. Shall we? I need to have a lot of, oh, yeah. Well, okay, so maybe, someone says, they said it sounds, like it might be a bad idea. Maybe, I don't know, I mean, I don't know, you might say, well, why in the hell would he ask if it was such a great idea, let's just do it, right? Should I do it? Does anybody have any criticism as to why it would be a problem to do that? Okay, I'm gonna do it. Stand back, I'm doing it. But I somehow, in the back of my mind, I'm kind of feeling like maybe I shouldn't. I'm thinking maybe. Is it possible that it's not the thing to do? Okay, don't do it. Can anybody give me a reason why I shouldn't do it? I mean, I'm doing it unless somebody can convince me otherwise. I'm going to do it. Is there anything wrong with it? I mean, you do understand what I'm going to do, right? I mean, I hope people understand kind of what I'm asking here. Okay, I'm going to start doing it. Okay, here's the table. R, A, B. All right, I'm not going to make it 10. I'll make it 5. Okay. There it is. And I'm going to say create index number 1 on, let's see here, I got to get the right syntax here. On R. And okay, I'm kind of going to be honest. So I'll just say ACB. I'll say ACB first. Because I'm just kind of, I'm going to be kind of, uh-oh. Is that going to everybody? No, that's a private message now. Oh, I see. Somebody did a private message because they don't. All right, one sec. I just want to. Here's my first one I'm doing. So if people don't stop me, I'm going to do them all. All right, Zoom, copy, and then paste. I'm making that one, and then while I'm at it, I'll just do another one here. Why not? I'll do. See, and this one's different, by the way. I hope people understand why those two are different. Okay, somebody said something here. I suppose it's a con. So since it's always expanding, it will do a lot of unnecessary modifications to it. This is kind of close. This is a close observation, but it's not. There's a more kind of direct statement to make. I'll give you guys a hint. I mean, like I said, I mean, there's a lot of, it's a big database. It's got a million tuples, and we're adding a lot of tuples because it's very active. You know, it's like doing banking or something. So a lot of people are adding, you know, moving money around, et cetera, et cetera. But then they're also querying and getting, you know, they're putting different conditions on and getting, you know, doing queries out of it. So they're doing a lot of reads and writes. So here, let me just, while we're at it, I'll just add that one in too. Okay, maybe I'll do this one too. Okay, I think I'll just do. I'm kind of going a little hog wild here. Oh yeah, I got to make one with E. Gosh, I mean, maybe I should write a program that just kind of grinds them all out, eh? But that'd be an easy program to write. I mean, it'd be on the order of like 5. Basically, what would it be? 5 factor? No, it'd be like it's a. I can't remember the exact closed formula, but it's like basically it's an n choose r problem. So, but it's on the order of factorial. Does anybody? Should I do it or should I? Anybody? Why would this be a problem? All right, because the thing is that some people do this. What I'm saying here, it has happened. The people do this. All right. So let's say I do this. Let's say I build like 5 on the order of like, let's say I build 120 separate indexes over this thing. Okay. What's going to happen when I add a tuple? Now I have to add a tuple or update a tuple or delete a tuple. What's going to happen? Exactly. All right. So all the indexes need to be touched. So basically what it's going to do is it's going to really make the expense on updates go way up. Okay. So that's the main downside of maintaining too many indices or indexes, is that they all have to be maintained under updates or deletes or inserts. Okay, so all those indexes need to be maintained, and that could wind up really dragging, making things really drag on the writes to the database. Okay. Any other problem with it? I mean, that could be. So you might say, well, so what? So what? Like you were saying before, Michael. This database. Let's say the database happens not to be updated that much. Okay, then there's more of an argument for doing it. But still, then indexes do take up space. You know, they do take up space. All right. And then there's a final thing, but the spaces, I mean, I usually don't take those space issues too serious because, I mean, we're talking about databases here. So we just kind of figured there's always going to be a lot of disk space. I mean, you know, I don't care. But there's another thing also, and this, I don't know what the status is right now with modern implementations, but I know in the past it used to be the following thing, that if you present 120 indexes, then the poor query optimizer is going to be dumb and consider all those 120 indexes. And as it kind of explores the possible solutions, sometimes it can boggle in deliberation by taking in too many index definitions. Now, I think I mean, that's kind of an error in the implementation, but a lot of earlier databases, at least, didn't really, you could wind up really kind of causing the query optimization to kind of ironically spend way too much time deliberating because it had so many choices to make. Right. So I'm not really sure what the status is. It would be interesting to kind of to run an experiment on PostgreSQL to see if it boggles under too many index decisions. But at least it's a possibility that it's going to boggle. It's going to kind of have to consider too many choices. And that could also slow things down. So basically, the moral of the story, and I know maybe it was a little bit painful to kind of have me just kind of not give you the answer immediately, but the moral of the story is that you got to, there are some kind of intrinsic reasons why you don't just build many indexes. Okay, so it's you basically have a trade-off situation going on here. So it's not trivial, and I think Oracle these days is trying to kind of make AI optimization kind of solve this kind of problem. Whether that ultimately is kind of going to be the way that it gets done, it's a possibility, but still, a lot of times as a database administrator, you will kind of manually go in and decide what your indexing strategy is going to be. Okay, all right. Let's see. So I think we can kind of move on then. Yeah. So these tuning advisors are kind of things that kind of do that. All right, let's just go on then, and let's go to the second topic of today. We might actually finish early, but let's see how things go. We're going to go on to transactions now. So let me just, what on earth just happened? Stop share. I have to stop. I lost my chat again. Let's see. All right. Let's see here, and what I'll do is I'll do the following. All right, move this, close this, zoopy-doo. Yeah, and let's share the screen. Okay, so now we're going to come to another thing that as an administrator, this is something that you'll find highly used and worth knowing, and that is this idea of transactions. So a transaction, what is a transaction? All right, so basically the idea behind transactions is that you're, I mean, you have the database is going to be used by multiple users simultaneously. I mean, that's not always the case. A lot of times you'll have these kind of private databases. Most of the time, databases are being used by many users at once. And it makes no difference if all the people are doing are reading. So let's say I have a database up there like, just a giant database of great authors and books of the 20th century or, 17th, 18th, 19th, 20th century. And there's all the text in those books and all that. And then people are asking, queries, or queries are being asked by a system. They can fetch out like the PDFs and the text for all these great works of literature. And no one's adding anything. Everybody's just reading from it. So that's fine then. I mean, everybody's hitting the thing simultaneously, doing a whole bunch of reads. We don't even have to worry about transactions really, because nothing's changing. So everybody's just reading. We could probably like replicate things and make it so that everybody has kind of a private copy almost. But you take a database like a bank or like money transfers, that's kind of the quintessential example, or anything that things are happening dynamically. You're booking something, like you're booking, you're going in and you're booking like a seat on a flight, these kind of things. Well, the fact is that you have many users doing that at once, right? I mean, you could sit there. I mean, let's say we had that. Let's say I want everybody to kind of book a seat in like an exam hall or something or whatever. all of you guys could go into a GUI or something, and you could kind of all be like trying to book seats. And the fact is that you might at one moment see that, oh, this seat A1 is available. And then you go to kind of hit the select button on it, but then one of your peers actually kind of weaseled in before you and was actually able to complete the transaction. So then when you try to click on booking the seat A1, the system, either it says to you, oh, sorry, that was taken, or it just kind of goes a little flaky, it kind of blinks a little bit, and then it turns you back to like the initial page. And then you go in there and A1's not available anymore. And you think it's kind of, well, that's just a kind of a junky system. That's usually how they do it, by the way, with transactions, because they don't want to tell you that somebody else snarfled it in front of you. So they just kind of let everything kind of flicker a little bit. And then you say, well, where did it go? And then you see that B2 is available, and then you grab B2. All right. So that's an example of transactions in the real world, because you have multiple people going in, reading and seeing what's available, and then trying to book things, right? And not everybody, another example was just like anybody who wants to book A1, I'd say, you got it. But then A1 is overbooked, right? Or even worse, I told all these people they had A1, and the only one who actually got A1 was the very last person to actually book it. That's not good. That means that updates are being lost, and a whole bunch of people then are going to show up at the exam hall, and they're all going to try to squeeze into seat A1, and they're all going to say, what on earth? I booked it. No, I booked it. And then, it's going to be a problem. So, somehow or another, we have to regulate this. Somehow or another, we have to kind of make it so we can have multiple readers and writers, and that people can at least make sense and be kind of rational as to how things get resolved. Right? Okay. So that's the kind of I hope that motivates at least why transactions are there. So, you probably have some experience with kind of transactional type stuff, like with operating systems. So let's say two of you, what happens right now? I don't know. I mean, if you use Emacs, I know it'll give you a warning, but other editors, let's say that you guys are working over a file system, you and your partner are working over a file system. You open a file, you start kind of pounding stuff into that file. They open the same file, they start pounding stuff in that file. You save your copy, and then they go to save their copy. What happens? I mean, I guess it depends on the editor. You know what a really bad editor would do? It would let the second person save and clobber right over what the other one had saved. Right? That would be bad. Right? So modern systems are probably not letting that happen so much, but still, at the level of the file system and the operating system, it's got a much weaker notion of what a transaction is, and it allows for things like this to happen, for things to be written over. So databases have to kind of keep a little bit more control over things. So this is kind of a good example from banking, would be that, let's say you and your partner or friend or whatever, you both have like a joint account or something, and one person goes and they say, okay, I'm in Stockholm. You guys call in and you say, okay, the one's in Stockholm, the one's in Umeå, and you both go right to the ATM, to the money machine, the bankomat, and you only have 1,000 crowns in the account, and then both you guys on the split second, you both withdraw 2,000. Well, you both withdraw 999 crowns. So you figure, well, if you're lucky, you'll be able to get an extra 998 crowns out of the bank without, it's not a very wise. It'll hurt your credit if you do this. The bank wants to make sure that doesn't happen, right? That they want to control for that. But in this case here, so it's you and your partner take out $100 from different bankomats at about the same time. The database manages to better assure that one account deduction doesn't get lost. So what would be nice for you guys would be the following thing. That is that, let's say that we have two people. We have A and B. Alice and Bob, I think, is kind of like, that's the classic thing. Alice for A and Bob, B for Bob is B. All right. So I just think of this way. Alice takes out $100. Bob takes out $100. Well, Alice, what her transaction is doing is it reads what's in the account, right? It says 100, or it says, let's say it says 500. So what's in the account? Okay, 500. Let me take away 100. Okay, so that means that what Alice's transaction is going to do is it's going to write back into the database 400, because that's what $100 being deducted from the 500 is. Now, at the same exact time, Bob is doing the exact same thing. So if they're lucky, what will happen is that the way things intertwine is that they both do the read. They both see 500, and then Alice writes out 400 because she took $100 out. And then Bob writes out 400. Okay. So what happens, that means that Bob's writing out a 400 clobbered Alice's. I hope that makes sense. So that's called a lost update. So Alice's update was lost. And in this example here, it's to the advantage of Alice and Bob and to the disadvantage of the bank. But the bank is going to now have a bad accounting system. Everything's going to be, so the bank will not allow that to happen. The bank cannot tolerate having a lost update, obviously. All right, so the way this gets done in databases is things are going to be grouped together as transactions. All right, so transactions wind up being, as it turns out, transactions, this is actually kind of one of those, this actually won the Turing Prize, the Turing Award. So this is like the highest award in computer science. Basically, what Tim Gray realized was that all you have to do is consider the reads and the writes. It doesn't matter. The intricacies of the transaction are not relevant, actually. It's just the reads and the writes. So if we have an account, right, let's call that X. Then the way we can model this is we can model Alice's as doing a read of X and then a write of X. And we can model Bob's transaction as doing a read of X and a write of X, right? So let me just write this down and look a little bit. So what we have here is we have read sub 1. Okay, I'll say read sub A of X, read sub B, Bob of X, write sub A of X. 1 second, it's coming. And write sub B of X. That right there, I hope everybody sees that thing right there. That is a schedule of operations of two transactions. There's a transaction A and there's the transaction B. Alice's transaction and Bob's transaction. X is the account, all right? Alice did a read, Bob did a read. Alice did a write, and then Bob came and did a write, and in doing that write, he clobbered what Alice had previously written. All right? So this is a bad schedule. This is what's called a non-serial schedule. All right? So let's think, what do we now, how about this schedule instead? I'll just do a different one. Oops. So this one, in this one, this winds up being a serial schedule. So in this schedule here, what we have is we have Alice reads X and then Alice writes X. All right. So now what happened is that it went from 500 down to 400 now. All right. $500 to $400 because she read X with 500. She took out $100 and then she wrote it back as 400 because the $100 was taken out. Bob then reads X, and when he reads it, it's going to be 400. And then when he writes it out, because he's taken out $100, it's going to be 300, right? So this is what the bank would much prefer, that things get done this way. So the bank would much prefer that the actual schedule of operations here are serial, that we have or serializable ultimately. Well, don't worry about that distinction right now. But I hope that makes sense, that second schedule there is something that actually does make sense in the world, okay? It actually, money's not going to get lost on that second one, right? It's going to make sense for the bank. It's going to make sense for both parties. And well, if that makes sense, then we also have this would make sense. I'm sorry. You can't paste into these things. All right, I'll just say it verbally. That serial schedule of Alice going first and then Bob going could also be read sub B of X, write sub B of X, and read sub A of X, and write sub A of X. So it could also have been that, right? That would also make sense. And that's just the one where Bob goes first instead of Alice goes first. But those two schedules, those 2 second schedules are perfectly A-okay. But the schedule at the top where they interleave is not good, okay, for the bank. So we're going to come back and we're going to talk a bit more about this. But let's take our break now for 15 minutes, and we'll be back at 11:15. And put any questions in the chat, and I can address those when we come back from break. Okay. All right. Let me pause the recording, which means I have to stop the share, and then I pause the recording. Okay, we got some, I guess, yeah, good. 11:15. We got some good questions in the chat here. The one question, I just repeated a lot of these questions from people who were asking privately, but the one question was, well, what about Alice reads X, then Bob reads X, then Bob writes X, and then Alice writes X. This is not going to work either. And this, what's going to happen there is that in this case, Alice is going to clobber Bob rather than Bob clobbering Alice. So basically, Bob, his right is not going to survive. It's going to be overwritten. And then somebody asked a very, very kind of good question. A very good question that we have a very, very direct answer to. And it's very important that you see that this is the way it is. Does a write on the value given by the read, or does it write on the current value, like current value in the database? It writes on the current value read. So in other words, I'm a transaction. I have my own internal logic. I do a read at time t, right? I'm going to base my decisions about how I write based on that read, all right? But in the intervening time, somebody has written out that I did a read of X, somebody has written out X. So at the time that I'm actually doing doing an action based on my read of X, it's based on what I actually read, okay? Not on the actual true value. If I want the actual true value in the database, I got to do another read, right? But then before I do another write, somebody might weasel in front of me and have already done a write. So the point is that these things are copied into, these reads are copied into the transaction's local memory, right? So it's very critical you see that's the case. That's what's going on in this model. And what's nice about this model, though, is that everything can be modeled by reads and writes, which is really kind of quite interesting, because you can have all these complicated things like, well, if the value of the account is above a certain amount, I'm going to compound it by 10% or whatever. That kind of thing. Well, I mean, maybe, if you think from the customer's point of view, that doing the withdraw, we have 2 transactions. We have the customer's transaction of withdrawing a certain amount from the account, and we have the bank's transaction that says, if the amount is above a certain amount, then I'm going to give you 10%. I mean, no one gives us anymore, of course, 10% interest. Now, it's in the bank's advantage that the customer first does the deduction and then they do the calculation. It doesn't meet the threshold and they don't do the compounding. It's in the customer's interest that the bank does the transaction first, compounds it, and then they do the deduction, right? But the thing is that both make sense. Both are, now we're not going to say which one, both running first the deduction, running first the withdraw and then the compounding is just as, quote, valid as running the compounding first and then the withdrawal. They're both valid in the sense that they both make sense. They both can be explained and say, well, that's kind of what happened. But if we intertwine them in some really weird way and we clobber and we ruin data, then it makes no logical sense. And that's what transaction processing is trying to do. They're trying to avoid that case of making no logical sense. And the beauty of the transaction theory is that you can just do all this based on reads and writes, which is kind of remarkable in some sense. So that's kind of the insights behind the theory of it all. In any case, there was another question though. That what about Alice reads X, Bob reads Y. Now, Y is a separate value than X. Then Bob writes out Y, and then Alice writes out X. So in this case here, there's no problem because they're not touching the same data item. So you can allow for any type of interleaving in that schedule. And this is actually kind of where transactions become kind of powerful, because if I always wanted to make sure that everything made sense in my database, like let's say that example, if I wanted all you guys to book rooms for the exam, or I'm sorry, book seats for the exam. Here's a way I can make sure everything makes sense. I'll say, everybody form a line. And then the first person can sit down at the computer and they can then book their room. They go, and the next person comes and they book their room. That's enforcing a serial schedule over all of you. But that's kind of like, where's the speed up in that? There's no speed up, right? There's no way that I'm allowing concurrent access. If I allow concurrent access, maybe like some of you guys will like, be booking like B17, another person B14. Those are all separate data items, right? So why not just let everybody edit, and those people who tangle up on A1 or any particular seats, we can run transaction processing over those contended, or those data items under contention. But when there's kind of this parallel access to individual items that there's no collisions, just let people at it. Let them have at it, and that's what transaction processing can actually provide. So it's very, very practical in that sense. I mean, it's necessary. So it's one of the big advantages actually of relational databases is they have a very mature transaction processing capability. Okay, so are there any other questions? This was just kind of more just to kind of get a sense of kind of what's really kind of going on. This is the kind of the basis of it. So it's fairly involved. And again, the advanced database course, we really go through transactions, in a deep way. So if you're interested in this stuff, definitely take 5D187. All right, so let's just kind of finish. Let's kind of give you a little bit of a working kind of knowledge though of transactions. So. Transactions, the main properties I'm sure many of you have heard this before, it's called ACID, which is basically transactions need to be atomic, consistent, isolated, and durable. This is kind of these are the ACID properties of transactions. Interestingly, there's a more modern version of this, which is called base, which is basically available soft state. It's more of a distributed. So for instance, Facebook will run on something called base. So let's say that you take your Facebook account and if you even have one, you log into Facebook here in Umeå on their servers, and then you tunnel through and you log into California. And at the exact same time, you change your interest. In the first case, you add tennis to your interest in Umeå, and then you add basketball to the one that you tunnel through for California. Somebody in Arizona reads about what your interests are. They're probably going to see basketball first, and then a split second later, tennis is going to get added on, right? But what they saw for a split second wasn't really consistent. So you could, with things that are so trivial like interests and stuff like that on Facebook, I mean, who cares really? Stuff like that, you can kind of have a more relaxed version of transaction processing because it doesn't matter. But when you start doing stuff with money or critical operations, then it does actually matter. So then you go back to the ACID. You go back to ACID properties of transactions. So what's ACID stand for? A is atomic. So if you have a big transaction where you're going to move a whole bunch of different things around, like the one big logical transaction is I'm going to move I'm going to move all these the amounts of this money from this account to that account, and I'm going to do. But before I do that, I need to check certain things. Certain things need to be true. I do a bunch of reads, and then I'm going to do a bunch of writes of money from one account to another account, etc. You do not want a situation where that thing kind of halfway completes and then it aborts. And so it's kind of, you kind of ran it halfway and now you're really in an inconsistent state. All right. So a transaction is going to have to either fail completely or it's going to have to succeed completely. There can be no intermediate state. It has to, and by the way, just to kind of say that when we talk about transactions in SQL, what transactions are is they're basically, you say begin, and that starts the transaction. Then you have a bunch of inserts, updates, or deletes, or select queries. Those are your reads and writes. And then at the end of that thing, you say commit, all right? That's a transaction, the begin and then the commit. Whatever it is inside that thing had better either had better fully execute or not execute at all, all right? I hope it makes sense to people why you would want that, because otherwise it's going to be a nightmare in terms of like, well, how are you going to fix it? How are you going to fix it? Once if it kind of got halfway through and then aborted, right? Consistent. Okay, so this is like the database. The foreign keys, the primary keys, all that stuff. They need to still be respected in the beginning state of the data of the transaction and at the end state of the transaction. So you have to keep things consistent in the database. Isolated. So isolated is a little bit of a kind of a deeper concept. So let's just skip isolated for a second because I want to explore isolated kind of in a more fundamental sense in a second. But durable. Durable means this. Durable is very important. What durable means is if I do a transaction and I commit, all right, and the system says to me, bravo, yeah, you did it, you're done, right? I better not come back later and find out that it was rolled back. All right. So it's like this. I go into the system, I book a seat. The system reports back, seat booked, committed. I'm happy, I got my seat booked. But then later on in the day, the system decides, oh, actually, I don't want to let that transaction that I already told Minak that this transaction was committed and fine, but actually I want to roll that thing back because there's some inconsistency has developed. That is bad, 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 bad. Because I left with the impression that it was a done transaction, right? So durable means that once it commits and once the system accepts it as committed, it's been run, okay? There's no backing out, right? So durability is one of those things where you almost always want. Now, when you get into the theory, you can see why in certain cases where you have what are called cascading rollbacks, and that will violate durability. So you don't want to have protocols that allow for this cascading of the rollbacks all the way back to, you got to at one point say it's done. And there's other things involved with the durability here. Like, for instance, durability has to do with like going to checkpoints. So in other words, remember, there's always the possibility that the power gets shut off to the computer and everything in main memory kind of gets zapped. So when you do actually commit something, you've got to make sure it's written out to disk, all right? Or at least the log of it is written out to disk because you need to be able to recover it. Now let's get back to isolated here. So what isolated is, actually, this is kind of a fairly deep notion here in a way. Isolation is the idea that the person who's using the database should really feel as if they're the only user of the database, that they're isolated. They don't have to worry about other people, all right? So in some sense, you can say modern society is built on a notion of isolation. A lot of people complain about this, but actually it's kind of a beautiful thing in a way. That is that you can go about your business as if nobody else existed, right? It makes things a lot simpler. And it gives people kind of a feeling of more power that they don't have to consider. They're basically isolated in a sense that they can do their transactions, they can do their business without any concern for other intertwining parties, okay? So that's what isolation is in databases. And the things, you never get perfect isolation because, and the same with society, you never really get perfect isolation. It's never really going to be, you're never going to, if there's more than one user, you're never really ultimately going to be perfectly isolated. Because it might be that you're sitting there happily working along, feeling isolated, feeling completely, well, I have the full access to the database here myself. I can move things around, do whatever I want to do. And it may be that the thing that's controlling concurrency might then just say, oh, and then you just got aborted. It aborts you, right? And you might say, well, why did that happen? Because things can't be perfectly isolated. Because maybe you were contending with somebody else over some resource, and the transaction manager decided, oh, no, I cannot be consistent. I can't have this thing go through without having some kind of lost update or putting the database into some inconsistent state. So, but certainly you would like to have it so you appear isolated. So the isolation, this gets controlled by the isolation level, all right? And we'll see that there's going to be various isolation levels you can pick for transactions coming up. So so this is just what I said before, that you have to begin, you do your operations, your SQL, and then you commit. You can also abort in the middle of it. You can self-abort. You can say, I started this thing, I looked around, I'm not going to push this transaction through, I'm going to abort. Maybe I'll restart later, but I'm going to abort. So yeah, I mean, your program can have a problem with division by zero, but it might also just be that you did a read of X, you did a read of Y, and then for you to push to move the money from X to Y, something else has to check out like Z. You read Z and it doesn't check out, so you're going to now abort because you don't feel like you can go through with the transaction, right? Or you sit there, like you got the system kind of set up, and you've kind of like selected on, you put your name in, you put in where you want to fly to. You're sitting there, and you clicked on the seat number, and then you're scratching your head, and you're thinking, actually, I don't want to go on this trip, actually, because I don't want to get COVID. So you say, and you basically abort. All right. So now the thing is that maybe soon we won't have to do that. So I mean, I actually, the truth is, I really want to travel, but that's why I come with that example. But I'm afraid the COVID. But okay. Yeah. So you can abort the transactions. So I think I've already kind of covered this business of the problems that happen when processes interact bad. This is an example in the slides you can see where if you got Sally and you got, Sally and I think, was it Bob or Joe? Sally and Joe. Sally's looking for the max price of a beer and a min price of a beer. And then Joe is actually going through and changing what he sells. And you get a situation where you get max is actually less than min. So, you get this crazy intertwining. Then there's this issue of like a dirty read. So dirty reads are bad. So for instance, what'll happen with a dirty read is that, let's say transaction A starts out, it reads X and it writes X, and it's going to do some other stuff. And now I'm another transaction, and I read X from what the write that transaction A did, and then I do an operation, and then I write something else out, and then I commit, and everything feels great in the world. Meanwhile, the other transaction is going along, merrily going along, and then decides to abort. That means that so transaction A starts, let's say Alice starts, I'm Bob. Alice writes out a value for X. I read in X, I do some calculations, I write out Z, and I commit, and I feel happy. Well, and the system says, you're committed. And I said, well, because of durability, I feel great, because now it's gone through. Now, Alice goes on doing other transactions meanwhile. So she's going on into the future. I'm done. I go and I'm taking a break now. But as Alice is doing those things, then she aborts. Something goes wrong and she aborts. That means that my read of Alice's write was a dirty read. Okay. And that means that, strictly speaking, I need to get rolled back. All right. The database is going to be in an inconsistent state. So a dirty read dirty read cannot be tolerated, because a dirty read destroys durability. Okay. So if you follow the thing about durability before, dirty reads destroy durability. All right. So you can't have that. All right. So basically the solution, we've already kind of talked about it. The solution is to basically try to put things into different, is to have to have the database police things so that not crazy stuff can't happen like that. There's certain policies that get put into place so we don't allow for lost updates and dirty reads. Okay. it's quite a bit more complicated than that, but this is kind of just kind of an overall sketch of what happens. So the isolation levels are kind of where this happens. So there's really only truthfully speaking, and this is actually, yeah, this is the way it goes in PostgreSQL. There's really only two, well, there are three basic isolation levels, right? Now, the way you set these isolation levels is you basically say set transaction, isolation level, and then you say serializable, or you say read committed, all right? Or you really live dangerously, and here's the easiest thing, the simplest thing to do with transactions, and that is just forget about it. Just don't even do it, and just let all these different processes go at the database willy-nilly, and just do whatever they want. All right, who cares? Now, there's some applications where you do that. You don't even care. You say, I mean, if everybody's doing just reads, then yeah, you do it that way. But even if they're writing stuff, it's kind of like, this is not the most important thing on earth. So, if it gets inconsistent, who cares? There might have applications where you don't even do anything, but anything with like banking, anything with money or booking, you need to have some kind of control, right? And you really have two choices ultimately. I mean, it used to be with database systems, there were more nuanced isolation levels. There's been a kind of a change in the architecture about how transactions get implemented because of, almost all database systems now are doing what's called multi-version concurrency control, whereas earlier in history, people did single version concurrency control. And the single version concurrency control was basically because memory was it was a different resource environment. Now it's like we have so much memory that there's like it's almost all database engines now build things based on what's called multi-version concurrency control. And that basically makes it so that we essentially have, for the purposes of this presentation, essentially serializable and read committed are the two isolation levels that emerge now, okay, that are the legitimate ones. So these are the ones actually that you should like focus on, serializable or read committed. All right, so let's see here. So what read committed does, let's see here. So let's first of all, let's just go under serializable. So what serializable says, if you say that all your transactions are going to run under serializable, what that means is it means that the database is going to be really the database is really going to be watching very closely what happens as the transactions unfold, and it will only allow transactions through if they correspond to some type of serial schedule. And when I say serial schedule, I mean a schedule in which things are absolutely equivalent to some ordering of the transaction. So let's say we have three people, right, who all want to do their business over the database. How many possible orderings are there of three people? And now I'm talking about like this business of me sitting there saying that I'm going to make things serial by basically taking these three people and saying, and they all have the three different transactions, and saying, okay, person number one, you go first. Then person number two, you go, then you go, and then person number three, you go. Okay, and that's like a pure serial schedule. That's a schedule that always makes sense, right? It always makes logical sense what happened under those. But if I have three people, three transactions, how many different serial schedules are there? Yes, very good. So 6. Yeah, that was the right answer. So it's the n factorial, right? That's the number of possibilities. Because you pick one of the three, and then you pick one of the two, and then you pick the last one, right? So 3 times 2 times 1. All right. So when you say you set the isolation level to serializable, now as we say before, we're not going to be so stupid as to sit there and order up our transaction and say, no, you must go first, then you, then you. We're not that dumb, all right? But what we're going to do is, under serializable, is we're going to make sure that we're going to control stuff so that whatever they do as they intertwine their operations, it had better be equivalent to one of those orderings. So as I have those three transactions, at the end of the day, when this whole thing gets done, it better be equivalent to one of those orderings, one of those 6 orderings. Okay, it has to be exactly equivalent to one of those 6 orderings. Now, what does that mean maybe? Let's say that person one and person two tangle in a weird way. I'm the transaction manager, but I want to make sure things stay serial. But I'm looking at the reads and the writes, and I see, oh my God, they're doing it again. So person one and person two are tangling up in a weird way that one of them is going to collaborate with what the other one's been doing. So what do I do as the transaction manager? I'm going to abort somebody, either one or two. I don't know which one. Maybe I'll have to decide, but I'm going to kill them. I'm going to come from above and just say, boom, and that's going to push them to the end of the line, right? Because I need to make sure. And so what that means, it means that in the ordering that person who I killed is going to be probably the last one to do their operations. All right. So that's just showing that you don't ever have perfect. They all might feel isolated until I bring down the club on one of them. Right. Then they're like, wow, okay, that one who got aborted, that didn't feel so good. But I got to make sure that it's equivalent to one of the serial schedules. Right. So this is actually the best. This is the idealized isolation level. All right. And let me tell you one thing. You better use it. All right. You better use it. If you're doing anything at all having to do with money, do serializable. Period. Don't. Now, if you go to something weaker, you go to read committed. All right. Read committed is a weaker isolation level. It's more tolerant. It kind of lets things go through. It's more efficient in the sense that you can have much more throughput of transactions, right? And all read committed says basically is that you can only read data that has been committed. So this dirty read we had before, where Alice dumps out X and then I read it, and then I do something and I commit, and then Alex later on aborts, and it was a dirty read, that's not allowed under read committed, because I can only read data from another transaction if that transaction has committed. Okay, so it rules out the dirty read, but it allows for other types of kind of strange interleaving. All right, but it's more efficient. You get more throughput. So there's a little story about this. The database vendors they all want to do well on the benchmarks. They want to do well. They wanted to do well on all the benchmarks that people run over them, and this is a stupid world we live in. A lot of them were defaulting to read committed. That was like kind of the default isolation level, not serializable, because then they would do worse on their performance. This is like, everybody wants to look good on the metrics, right? But there was a Bitcoin exchange that they were running their Bitcoin exchange under read committed because they got good performance, and also because that's just what the way the database came as a default, and they didn't really think about transactions. And the probability that the following would have happened is so remote. But basically, when we take the advance, I don't think I have the time to kind of go into exactly how it happens. But basically, well, the way it works is this. I open an account on this Bit exchange, and then I launch 100 simultaneous read committed transactions that all do a transfer from one account to another account. So I have two accounts on the system. So I have account X and I have account Y. Account X has 100 Bitcoins in it, or well, that'd be a lot. It has $100 in it. Account Y has 0 in it. I launch 100 simultaneous transactions under read committed, and they transfer $99 from X to Y. All right. Now, under read committed, as it turns out, I can have it so that X is going to go way into negative, even if the system is checking that accounts can't go to negative, and then Y can go into a very large positive. And then I can snarfle away and then transfer the Y out to another, remote account. And then I've just made a giant fraudulent move. Okay. Now, what's the probability that would ever happen? Now, the thing is, you can do that under read committed, but what's the probability that would ever happen? Well, here's the problem. The problem is if somebody knows they can do it, fairly high. So you cannot think in terms of transaction as like, oh, that's a worst case, that would never happen. Yeah, but you have an adversary in the world. You have scammers. You have criminals, right? So if a criminal can do it, they're going to do it, right? If they can make a profit. So you can't think in terms of like, oh, the probability that would ever happen is so low. If they can figure out a way, if they know they can do it, they're going to do it, right? So actually, that actually happened in real life to this bit. I guess this, I don't know all the details, but there was the story of this Bitcoin exchange that got BK'd on this, and they went belly up. But that's life. I mean, God only knows. But the issue then basically is that, well, are there certain cases under which you would want to run under read committed? Maybe, but be careful with it. Be careful with it. I think that in general, what you want to do is it's in practice, if you have transactions going on in practice, you want to stick with serializable, right? So there's some nuances to this that we'll cover that in the advanced course, but I just thought I would kind of tell you guys about that. Yeah, so isolation levels get set on each transaction. So it can get very complicated actually, because you can have some transactions that are running under read committed. You have some other transactions running under no transaction processing, and you have other ones that are running under a serializable. Then there's also what's called snapshot serializable, but we'll get into that in the advanced class. With those more, there's a little more nuance and kind of gradation in the transaction levels. But really, from your point of view here, in terms of this course, just think in terms of read committed and serializable, and stick with serializable, in implementation. Okay, actually, I think that's all I had to say now about all this. So, yeah, I mean, there's some examples you can go through on the slides, and there's, of course, the readings. So I think maybe we can then conclude at this point, unless are there any questions? I'll just wait here for questions. Yeah, I mean, transaction processing is pretty cool stuff, actually. I mean, it's very intricate, but it's good. It's good stuff to know, actually. All right. Okay. Well, so here's the plan for the rest of the course now, I guess. Recitation makeup is going to be on Thursday. Oh. Yeah, I have a question here that I'll just, it came private, I can answer it publicly. So, and I think I'm actually in the process of answering this right now. It has to do with the exam. What's the plan now? So recitation makeup is this Thursday. Then we're going to have like a review lecture where you guys hopefully will have a lot of questions. I'll publish the older exams. I know I haven't got around to that. I'll publish those, and I'll send out an email when I got those out there. The thing is, it's a little bit different. Usually the way I would run exams before is I'd have them closed book, because that would force you guys to read. But I can't do that now because we're going to be doing things it's going to be over Cambro. And then, of course, there's the whole honor system. You guys aren't supposed to cheat, I mean, go read the honor policy, or just be honorable. I mean, I think that, well, yeah, I mean, we have our ways to figure out if things are really kind of weird. We reserve the right to turn into an oral exam, by the way. That is absolutely our right. If we suspect something kind of weird, we reserve the right to kind of do an oral review of what of you guys. So that's just keep that in mind. So study and do it, play it right. But anyways, I'm assuming most people are honorable. All right. But basically the way it's going to work is that you guys are going to have a time. You will not be able to contact other people. That's kind of those are the rules, period. Basically it's going to be, you are going to be released. The exam is going to be released. It's going to be, there's going to basically, here's how I write exams. I'm going to, most of the stuff is going to be fairly straightforward. It might be kind of like some busy work, and you might learn something actually through that work. So there's the questions, and you have to kind of grind out the answers. So a lot of it is just kind of doing the work. And then I'm going to throw in a couple problems that are going to be hard, that are going to be kind of like, you got to think really, a lot. Or you got to, I don't make them that many, but I want to have a couple problems that are kind of like, I might even put a problem on there where I think, gosh, I wonder if anybody's going to get this. I know a couple of questions that no one ever gets. But yeah, I mean, so I might not put those on there because I've tried so many times and no one ever gets them. But simple problems that are there, they should be clear, but they might be hard. So I'll put like maybe like 10, 20% that are hard problems. So having a deep understanding is going to be, kind of thoughtful understanding of the topic is going to help. But otherwise, I mean, if you do your honest studying and you do the readings and you've done well in or you've done the recitation problems and all that, I mean, it's not that difficult to pass. But to get a 5, I want to make that a little bit hard. I want to make that kind of a little bit of a distinction to get a 5. But a 3 or a 4, I mean, if you do an honest, effort, you should be in okay shape for that. So the way it's going to work, of course, is there's going to be these, it's going to get released on Combro during the specific exam time, and then you are going to fill it out as a Cambro exam in your own private place, and then I'm going to grade it. And if we suspect anything, and I have to talk to them a little bit more. They've been talking about some ways to kind of get some extra technology in there to kind of monitor things or whatever. But I'll find out more about that. But I'm just going to, it just leave. You got to be. Anyways, I hope that you guys see what I'm saying here. The exam will look, I did have a Combro exam last year because that was just right at the start of the COVID, but that's not really, that was kind of a rush job a bit. I want to do a bit better job. So I'm not sure how much this exam is going to represent the earlier ones, but certainly looking at the earlier ones will give you a lot of indication. I'm not sure if that helps, but I mean, in the lecture, the final lecture, which is going to be exactly 1 week from now, not Monday, when I do a review, by that time, I hope that I have the exam written. So it's probably a good lecture to be at because I'll probably, knowing me, I might kind of let things slip a little bit because I get, excited and came in talking, and then next thing you know, I'm giving away the exam problem. Let's see here. Yeah, so I think that maybe the best thing to do is that when I put those exams out, what we're going to do is we're going to then discuss those. Probably the review is going to be mostly me doing these old exam problems in front of you guys. That's probably what it's going to end up being. So I'll definitely have the exam, the problems out by, as soon as possible. Definitely before, if I don't have them out by Thursday, I will. I'm going to try to get them out by tomorrow to have everything kind of lined up there. And then you guys can look over those problems and ask me which ones you want me to do in the review. But don't stress too much about it. I mean, it's mostly if you just do, I mean, you're going to get a 3 or a 4, if you do your honest work, and you might even get a 5. It might not be that hard, but I want to put a couple hard problems on there just to, to make some people kind of stretch a little bit. So are there any other questions? Yeah. Okay. Well, I mean, I'm just waiting to see if there's any more questions coming, but it doesn't seem like there are. Okay. Well, great. Yeah, I mean, definitely do the readings. That's one of the key things is to do the readings. So, okay. Well, with that, I bid you all farewell, and I'll see you on Thursday. I'll see some of you on Thursday, the ones who want to make up a recitation on Thursday. Oh, and also if you got like a recitation where you didn't get all the points, but now you want to go back and get all of them, you can do that as well. So you can, if you've been to all the recitations, but you're still missing 3 or 4 points from one of them and say, well, I want those 3 or 4 points, you can go into this recitation and make a claim. Okay. All right. I bid you all farewell. And then where is the, okay. End meeting for all.